Yeah, thanks a lot for the invitation. I'm really looking forward to be here for 3 weeks and yeah, interact a lot. So I hope I can contribute another perspective to this whole workshop. And this comes from Causal Inference and Causal Discovery. And yeah, with this, I would directly jump into this topic. So maybe to take a step back, what we do to learn about the phenomena, to learn about the underlying laws and the underlying causality that governs our world. In the climate system or in climate and earth system sciences, we are more limited than in other sciences. So what I show here is maybe the first time that the scientific methodology of running experiments, of reasoning about what we see, of coming up with explanations for what we see, can be coined to Galileo Galilei. The other picture I show here is that of Svante Arrhenius doing some experiments in a lab, maybe regarding the greenhouse gas effect, but of course, we cannot really experiment with the Earth on a large scale. Although I found this, there's like a scientific kit for kids to play around with weather and the Earth. And the other system that we have, the other approach that we have, are Earth system simulation models. So shown here is one of the first ones due to Manabe and Brian, which was rather simple. And of course, now we have much more complex models. And these are our tools that enable us to do experiments, to really reason about the world, the Earth, with a simulation of the Earth. And finally, we have observational data analysis and also some history here. This is a table of surface pressure correlations due to Sir Gilbert Walker. And today, of course, we have a large network of satellites that give rise to big climate data. So jumping directly to the before mentioned Manabe and Klaus Hasselmann, who both received the Nobel Prize this year in physics. And well, for their contributions to the physical modeling of the Earth's climate and quantifying variability and more. And Klaus Hasselmann, I just looked into a paper of him from 1993, where he was coming up with the statistical methods, the optimal fingerprinting, to really detect the climate change signal in data. And when you read it now, then it's really kind of an exercise in causal inference that he conducted without really, of course, knowing the whole theory behind it at the time. Another Nobel Prize of this year was in, well, it's not the Nobel Prize, it's the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel to Joshua Angrist and Guido Imbens for their contributions to causal inference. So quite incidentally that this year, both topics that I work on have been receiving this prize. But next to the Nobel Prize, another preeminent figure in this field is Judah Pearl, and he received maybe the Nobel Prize in the computer science community, which is the Turing Award, in 2011. And in 2018, the deep learning community got their prize. And yeah, today we will talk about Earth system sciences, causal inference, and machine learning more generally. So these two topics receive quite an attention inside the machine learning community, causal inference and machine learning. So this is from a nice overview paper of Bernard Chirikov and many others that it's a little bit hard to see here, but that coins really that the concept of causal inference is a crucial cornerstone of machine learning to overcome a lot of problems regarding transfer and generalization. But of course, also this goes in the other way round. So to maybe coin it in one sentence, causal inference is really about identifying assumptions and methods that enable to learn causal relations from observational data. So the theory that he laid out in his book, and this is a popular science book that is quite nice to read here of Pearl, has been developed not just by him, but also by other people like here, Peter Spiritus, Clark Lima, Richard Shines from Pittsburgh. And their theory is really about how we can reason about causal relations, given that we only have access to observational data, under which assumptions are statistical dependencies linked to causal relations. So today I will cover a bit of these topics. So I want to start actually with a toy model that I've hacked in this morning and last night, because I think it may give an intuition of how causal inference can help in the topics, for example, that we discussed yesterday. But first, to lay the foundations a bit. So causal inference assumes that we have given data, and here in our case, this comes from either observations, observational data, or from maybe simulated data, as we've discussed yesterday, maybe from high resolution models. And the climate system is, of course, not just linear on climate scales, but nonlinear in many dimensions. And the cornerstone underlying causal inference is assuming that there's an underlying causal model that governs the data, that gives rise to the data that we have. And here, in a time-resolved manner, we may write it maybe in this way. So we have our measured variables, and we need to assume that there's some underlying dynamics governing them. For example, x1, the time t here, is some function of the remaining variables and some noise that we model as describing the unresolved processes. And the same for all the other variables here. Now, what often might be the case is that in physics, you might say that, well, one function is only caused by causes precede effects by the past of other variables. But of course, when we deal with real data, we may have aggregated data that is on a coarser time resolution than maybe the underlying physics. And therefore, in causal inference, we often have the problem that there might be contemporaneous relations. And that's how I denote this here by this variable xt. So each variable here might also depend on contemporaneous variables. But this is maybe too large too dense of a network, because here we kind of write down a function how one variable depends on everything else. While what we may reasonably assume is that only a subset of the other variables, here denoted by this p indicating the parents, are really the causal drivers of one variable. And if we make this assumption, then we can write down what we've written down here as a causal model, a structural causal model, in the form of a graph. So there's always this association of an underlying structural causal model and a graph, where simply the nodes are the variables of interest, in the time series case potentially at different points of time. And the arrows, they are just occurring whenever one function or one variable appears in the argument of another one. So this is a qualitative picture of the full functional dependencies in the structural causal model. I mentioned there can be time lags. You would have to represent this graphical model in a time-resolved manner in climate science, typically, with lagged and contemporaneous relations. So, for example, if this is the graph, then the according structural causal model would look like this. So x1 here depends on x2, and x2 just depends on maybe the noise. So x3 depends just on x2, and so on. Now, what is the causal effect? If you have now the assumption of this underlying structural causal model, then the contribution of Pearl is really to mathematically formalize what it means to intervene in a system. And quite simply, it's, as he coins it, doing surgery on the model. So you intervene in the model by replacing the equation for the intervened variable by whatever you set that variable to. So here, before the intervention, this was the model equations, and now the this equation for x3 is just replaced by x star. And graphically, this can be visualized as deleting all the incoming edges to a node. And then the causal effect is really how this changes the distribution, or what the interventional distribution looks like. For example, here, x4, how does the distribution of x4 look like if we have intervened in x3? And that means really changing the equations of the underlying system. So this graphical model also gives rise to dependencies in the data that I will discuss later on when it's about how can we learn such graphical models from the data alone. So I'm now showing you some little toy model that may give you an intuition on the relationship between what we use in machine learning, or what we use as input more particularly. So assume that we have as ground truth underlying the causal graph down here. So you have x1 and x6 as causal drivers, and then the other variables, they are not really causal. I mean, x2 is an indirect cause of y, but x3 is just correlated with y due to the confounding from x1. x5 is just unrelated, and x4 is a descendant of y. It's caused by y. So we have some structural causal model that describes these relationships. Now, if we want to look at the causal effect, we would intervene in the data here, xt, x1, and we set it to some x prime, some x star here, and do that maybe for different values of x star, plotted here in this scatter plot. And then the black line is the expected value of y, given that intervention. And for this data set, this is just linear here, as you can see. And this makes up now our ground truth. It's just a linear model, really. So how can we, as you say in causal inference, identify this effect from the data alone? So now we assume we just have given data from the system. We don't have the ability anymore to intervene. But we know the graph. We know the qualitative causal relations. And now, most intuitively, right, if you know that y is a function of x1 and x6, well, you fit a model on x1 and x6. And if you do so, then what you actually get is this, well, the red line and the little band is the uncertainty around it. You get an unbiased estimate of the true causal effect. But what happens if we do not know the qualitative underlying causal relationships, but we just have these other variables and we just put them in a model? So what if we include all inputs? So we fit a model of y on all the other variables, just because we either don't want to assume some underlying causal relations, or we just don't know. So if you do that, then we obtain this blue model of y. That's the prediction for y as a function of x1 in the fitted model. And as you can see, it's wrong. It's a biased estimate. So not even the expectation is consistent with the ground truth. So why is that? Actually, why is that? Any idea?
Those are not independent covariates.
They're not independent, right? I mean, most particularly x4 here is one that is dependent with the others. It's not super important that they're not independent. For example, x3 and x1 are not independent, but that's not the main issue. I will show that in a minute. But the real issue here is that we condition on a variable that is actually an effect of y, a descendant. So we basically, while we are interested in the effect of x1 on y here, but by conditioning that on whatever value x4 takes, we bias the effect away. We change it. And that leads to this biased estimate here. So maybe we have a little bit of side knowledge and we know that, well, x4 is actually caused by y. Maybe we have this knowledge. So we remove this x4 from our regression model and just include all the other variables. And what we get then is actually an unbiased estimate, but with a large variance for now. So we now exclude really all variables, except for those where we really know that they are caused by the target variable, y. So now our variance is very high. The variance gets even bigger if we consider the following. The little change I've made here is that the training data was a different type or different data set than the test data. So what if in the test data, we have a shift in the variable x5? It's just shifted plus some additive constant. So interestingly, by including that, even though there is no causal relation, by including that in our model, we get a much larger variance. It's still somewhat unbiased, but we get a much larger variance around our ground truth. Another example, what if we know we only want to include all variables where we know they have a causal effect on y? It's just that we don't know whether it's direct or indirect. For example, in this case, x2 only has an indirect effect, but maybe we don't know it. Then we get a much smaller variance. We get a much better estimate of the causal effect. Now going back to the causal model, what if we only take the two causal drivers and do again the experiment of having a shift in x5? Well, the estimate is the same because we haven't used it in our analysis. We only took the causal drivers as input, and that prevented us from fitting a model to the variable x5, which gave a little bit of a relationship here. And then in the test data, we had a big shift in x5, and then the model thought that y had to also change. So we avoid this bias due to a distribution shift if we just use the causal model. On the other hand, if we have a shift in one of the causal factors, then we actually want to see a change in the ground truth. So that's what you see here. You see a change in the ground truth, and this is also correctly estimated by the causal model. Now, I've used linear regression in all these examples. What if deep learning is somehow smarter? What if deep learning, in this case, just a multi-layer perceptron, maybe that figures out somehow how to treat these variables. But it doesn't. So the effect is still biased because we condition here on x4. We include a descendant. What if we exclude these descendants again? Well, we get a little bit of a better estimate, but it looks shaky. It's a linear underlying ground truth. We fit it with a neural net. It's overkill. It's trying to adapt to just a small sample size here. Well, I mean, it's not quite as good as in the linear case. What if we regularize it? So I'm really just playing around with the scikit-learn regularization parameter. And then it gets better, actually. And what if we go from a shallow to a deeper, just more hidden layers? Not sure whether it really helped here in this case. What if we now, again, only include the causal inputs? Then we still get a higher variance than using only the two causal drivers. So also here, the deep learning approach didn't help much. If we then again do the regularization, we get a better result. So fundamentally, the problems are not much changing if you use a more advanced fitting technique to the wrong input. But it may help. The regularization may learn that x2 is actually irrelevant. It may maybe with an L1 norm or so put that to 0, that input. But we cannot really be sure. that it learns that. Another thing I wanted to mention is, and which is current work of mine, what if there are other variables, and this bidirected arrow really means there is some hidden confounder of x7 and y. So x7 and y are sharing information.
So are you assuming like the chain along the graph along the time is always connected as a chain?
So I mean, time doesn't matter much here. I just put the indices because we are usually dealing with time-dependent data, and you can include a variable at different instances of time. But this relation, for example, may be at the same time. X4 and X and Y may both be observed, or the sample may be at the same time.
Because like the time arrow decides like causal law, right? Because cause always happens before the consequence, and that there's like a structure that's already embedded in the graph, right? Yeah.
So when you that's when you know that maybe this variable you have maybe some side, so you wouldn't include variables in the future in your model. But at the same time, this can still happen that you condition on a descendant. But if you just condition on the past, so if you strictly remove any contemporaneous variables, which may be, however, important causal drivers, then you only are in the setting that I showed before, where you have causal ancestors, but you can also have those correlated variables. So you don't run into the problem of conditioning on a descendant, which will always bias, but you still run into the problem of having increased variance because you condition on variables that are actually not causal drivers. So in all these cases here, the estimate is actually unbiased, but has high variance.
Just a quick question on the relationship between X7 and Y. Is that a feedback or the exchanging?
Yeah, so this really means that there's a variable L here, a latent variable, that directly causes X7 and causes Y.
Okay.
It's not a feedback.
Okay, thanks.
Sorry, one more question. Do you assume that the causation is stable in time?
So I assumed it in all the examples where I didn't do this distribution shift. So here, yeah, the data is completely stable, yeah. It's the same underlying equations generating the data. I'm just using the data and fitting different models, fitting different inputs.
Thank you.
But I mean, in this example here, where I intervened here, there I shifted the data, and that's why I got this bigger variance here. So there the test data was first sampled from a different distribution, where X5 had just a higher mean.
I think it was more related to if you have a different variables, X2, X1, X3, and so on, through time. This is how you establish the causality, right? What happens if you have more relationship with X6 at the beginning of the record and more relationship with X1 at the end?
Okay. So yeah, it's assuming that the distribution is stationary over the sample that you choose. That's right. Otherwise, you cannot deal with it, or you have to do some other advanced stuff. Yeah.
Thanks.
So what I wanted to mention here is that it actually, in this case, it helps to condition on this variable because it constrains the information in Y and makes the estimate more precise. It's not so big, largely visible here, but it's what I worked on. Now, another case is, what if we, now this blue line here comes from a model that just uses X1 and misses X6, which is now a confounder. So this is the classical example of confounding bias. We want to estimate the effect of X1 on Y, but in the data there's a confounder. It's observed. We just missed to include it in our analysis, and then we get a biased effect. We get an error. If, on the other hand, we include the variable X6, as in the orange model, then we correctly estimate the relationship. So to extend a bit, or to link you more to a paper that just came out or will come out on Europe's. This considers the problem that you are given a graph where you have hidden and observed variables, and these hidden variables are encoded in these bidirected edges, and you just have this background knowledge of such a graph, and you want to estimate the effect of x on y, and then this theory here tells you what variables to condition on in order to achieve the minimal estimation error, provably minimal, at least for some class of estimators, provably. And the paper contains a construction algorithm and so on. And although I can only show that this theory holds for estimators that belong to a certain class, I empirically find that using these variables as conditions in the model as inputs basically also reduces the variance in non-parametric settings, like with random forest, neural nets, and so on. So this might help to give less biased estimates or lower variance estimates of causal effects. So let me maybe stay here still, because I think to relate it, for example, to yesterday's talks, often what I see is that people just put everything in as input in a neural net, and then you hope to, by regularizing the functional form, the fitting procedure, you hope to achieve an unbiased estimate. And that's one approach. And the other is to use side knowledge on the causal reasons, on the causal effects, to choose a priori the inputs of your model. And that's this graphical modeling approach. And maybe sometimes you don't have that side knowledge. Maybe you cannot draw this graph. So you wouldn't know whether x3 is really a cause of y or whether it's just related. Maybe you just looked at correlations and they would be correlated, but putting in a correlated variable into your model might lead to errors, or putting a variable x5, which is maybe spuriously correlated. So causal inference here helps machine learning to choose the inputs of their models. And then you can leave it to the machine learning model to train a very complex function. So here I looked at linear models, but of course this applies to any type of functional relationship. So there's a nice kind of complementary synergy here. So I think that's the main point I wanted to bring across. I have worked a lot on causal discovery, which is, if you do not know the graph, how can you estimate the graph from data? And then, of course, you can use that graph in such a fitting procedure in a machine learning model. So observational causal discovery is a topic that you can read much more in this paper, written together with many colleagues from Climate and machine learning. And it covers methods like Ranger causality as one approach, with some shortcomings, which are overcome by the more general theory of graphical model learning. And I would rather give you a visual example here. But in essence, these methods use, for example, dependencies in the data, like conditional dependencies, to figure out which variables are direct causes and which are just independent given other variables. So if you make the assumption that if a variable is independent of your target variable, such as, for example, this one here is independent of z, maybe better to look at the ground truth here. This variable here, x at time t minus 1, is independent of z at time t given y at time t minus 1. If this is the underlying ground truth, then this conditional independence should be visible from the data and can be learned, and therefore you can remove this, or you can prune the graph to one that in the end looks like this one. And then you can use additional constraints, such that you assume that the model is acyclic, to even orient edges here. For example, here between two contemporaneous relations, we can still infer that that must be a causal effect from Z to W, because if it was going in the other direction, we wouldn't see the same conditional independencies. So the conditional independencies, they really are often leaving an imprint of the causal structure underlying. Different causal structures lead to different conditional independencies, and this can be exploited. Another branch of causal inference deals with the problem that here these two variables x, y cannot be really oriented, the error between them. We cannot say whether x causes y or y causes x in this case. Here we could, because we had these causal arrows inputting to z. So this is a collider here, and colliders are the basis of inferring orientations. So here we cannot use this. And to overcome this, the stereo or structural causal models uses further assumptions. So we got this graph from assuming that the causal relations give rise to dependencies and vice versa. And if you make further assumptions, namely that, for example, the functional form is linear or nonlinear and the noise is Gaussian or non-Gaussian, you can identify further causal relations. So for example, here, if x and y have uniform noise, then there is a certain asymmetry that you can exploit, which is exploited by the linear non-Gaussian acyclic model. And this asymmetry, really from fitting in one direction and fitting in the other direction and plotting the residuals against the potential effect, you see there's an asymmetry in both directions. And from this, you can infer the causal direction between these two. So interestingly, this does not work if the data is linear Gaussian, but it's an if and only if theorem. So whenever there's non-Gaussianity, this helps in identifying causal directions. Yeah, I may skip this part. You can really read more about causal discovery, the different methods and limitations in this paper. I think I could stop here because it's more interesting to interact more. This would just be about my methods that are in this realm and address particular challenges of high autocorrelation, of latent confounding, and further topics. I think I want to really show you the underlying foundations. We have, of course, quite some applications to different topics, mainly on teleconnections and seasonal prediction. Yeah, so I close here.
Okay, thank you very much. Very intriguing. Any questions from the audience? There was already some discussion, but there probably is a lot more. Ooh.
I have a question. If you wanted to combine this kind of causal graphs with symbolic regression, and move from a kind of probabilistic description of causality to something more like an equation, how would you mind like speculating on how you might do that?
Yeah, I think yesterday we had this sparse regression, for example, and this may partially help to identify causal relations. For example, it may help to find that x2 or so has no relation with y if you already have x1. So if you have an L1 norm or so in such a model, you can learn that and also learn the functional relations at the same time. But I would say that if you have x4 in your model for whatever reason, then also that approach would not be able to discern that x4 is actually not the right variable to condition on. It's a knowledge you can also only input from outside. You cannot really learn that from the data alone that the causation here goes from in this direction. I mean, you can learn it in causal discovery, but if you fit a model, then the model itself wouldn't be able to discern that.
Okay.
It's actually a recent topic that emerges, which is neural structural causal models. And they frame causal discovery, the other topic, as a continuous optimization problem where they have to first define the class of graphs they operate on, and then they have to turn the discrete optimization into a continuous one by relaxing and being more accommodating to different graphs that are maybe cyclic or so. And it's a quite upcoming topic now to try to use, to frame this in this optimization framework, and at the same time learn the functional relations and the causal graph. Yeah.
Okay. Hi. Very much for a great talk. My name is Maria. I work at NCAR, and I was curious to get your thoughts about events that maybe not only are rare in time, but also have a very strong signal. And so, for example, to be more specific, something like a volcanic eruption, and there's this hypothesis that it causes a certain effects on enso variability over time. So I was wondering what your thoughts are on how to quantify that sort of relationship. And so more on the causal inference portion of your talk. So a signal that's very strong that we really think produces something in the Earth system, but how would we go about calculating that in the causal inference framework?
Yeah, I mean, in this case, you have the side knowledge that a volcano cannot be caused by weather. And if you put that in, you can actually use this information to learn causal relations among other variables, because you know that the volcanic eruption, if you have a time series of, the amount of aerosols put into the atmosphere, then that is kind of a natural experiment, right? That's how you can consider it. And then you can learn whether that effect propagates through the atmosphere. And that can help you to learn about causal relations between other variables. You always know that the volcanoes can only be a cause, they cannot be an effect. And in this way, this greatly helps. But in the end, it would just be another node in the graph that describes this volcanic variable. And maybe it's just because of one incident, a very small sample size, and it doesn't help so much. But if you use many of those volcanic eruptions, that can help.
Thanks for the great talk. My name is Pedram Hassanzadeh. So in the slides that you were going through at the very end, you had these methods that allow time lag versus assumed time lag. So I don't know whether my question is related to that or not, but I'm wondering to what extent do you need time scale separation between the variables that you are looking at the causal relationship? So specifically, the application I have in mind is about looking at causal relationship between processes that are at synoptic time scale, like 5 days, versus at like low frequency atmospheric variability of 10 days. So this is pretty close. So I've seen very nice papers like by Libby Barnes and others on looking at longer time separations, but I'm wondering to what extent do you need time scale separation between these processes to capture causality?
Yeah, great question. It's to me, it's still like, because this is like a discrete node description of the variables that are tied to the time resolution of the data. So here, TET minus 1, if your data is daily, then you would have a node at each day. And you will get a different graph if you take a different time resolution. If you take the monthly time resolution, then in principle, if you have an underlying ground truth like this and you average the data, you will mix up stuff. Like you will basically end up not with a finely separated structural causal model, but you lead to like a non-Markovian model in the end. So that mixes up stuff. Of course, that's like the strict theoretical view. Approximately, you will still get somewhat Markovian relationships in the end. But actually, one PhD student of mine is working on this topic of timescale separation, like how we can use filters and how they interact with causal discovery, like using wavelets, for example, to better circumvent the problem that in this case you always have to define the time resolution and then you get a graph. But what if you just want to take the highest resolution that you get and better learn the causal relations and learn which timescales are relevant, for example. So we're working on that.
Thank you. Any other questions in the audience?
So if if you run this kind of method like the PCMCI or some method on a global map and you find some regions that do indicate causality, but like neighboring grid points don't indicate causality, how do you interpret? So for instance, like if you take an ENSO index and run it through PCMCI to find grid point relationships, right, rather than averaging over an entire domain, and you find noisy maps that come out that indicate causality in one grid point, but not in a neighboring grid point. Do you have techniques to physically interpret what that would mean? And like, how do we physically understand such causality if it's not like a large scale mode or a EOF or some kind of an average?
Yeah, great question. It's the question of on what nodes, on what variables do we actually do causal discovery? And I'm not solving this here. I leave it to the user to define the nodes of interest, and I just address the problem of getting the graph among these nodes. So this is in a similar direction as learning the time resolution. It's learning a spatial dimension reduction. And this can be termed as causal representation learning. And the Jakob paper in the beginning also talks about this. So how can we integrate that? Like learning the dimension reduction at the same time with a causal graph. But because you mentioned grid locations. So if I think of the East Pacific and having one node there and learning the causal, like putting that as a node and learning its relations with, I don't know, Peruvian precipitation, and having as another node the neighboring one degree apart, then what you assume in causal inference is that these are two autonomous processes. While I would kind of challenge that they are autonomous processes. They are part of the East Pacific ENSO system, and it's kind of artificial to just consider them as different processes. So in Perl's language, you have to assume that you could intervene in the system without changing others. And in this case, I would say you can't. So it's maybe like this is not the right graph to consider.
So you would recommend doing dimensional reduction with our physical understanding of the system
Yeah,
before
definitely.
you do the causal discovery?
Yeah.
Okay, thank you.
Any last question from the audience or from the people online? If not, maybe you mentioned Hasselmann's optimal fingerprinting method in the beginning. So how does that fit into this framework, and how could it be improved by these methods?
Yeah, I mean, I just looked at it last night, so but it's like an instrumental variable approach, because you use the predicted signal due to the forcing from the climate model, and then you regress by the maybe regional variability of some variable, and then you regress your global mean temperature just on this predicted signal coming from the forced signal, and relate that to the observed signal.
Mm-hmm.
And this removes potential confounding between global mean temperature and those observed variables. The idea is the instrumental variable idea. And you could improve that because causal inference, Perl has put instrumental variables in a much broader framework. So you can further, maybe in this optimal adjustment case, condition on other variables that may give a better estimate, a more precise estimate of this global warming effect, for example.
Yeah, it would be interesting to do. Yeah.
Yeah, I was having the same thought. Yeah.
Yeah. Okay. Well, thank you very much, Jakob. It was very interesting to hear it directly from you also. And I will go over to the next speaker.